Any other questions right now? Okay. Last time, what were we talking about?
Helium.
Yep, we were talking about the helium atom. We developed a Schrodinger equation, we had a generic Schrodinger equation. We expressed a Hamiltonian. To solve that Hamiltonian, we had to use the orbital approximation, but we haven't actually talked about the wave function at all, right? So today, what we're going to attempt to do is get to a point where we can describe that wave function. There are some requirements that we're going to have. We're going to have to know about determinants and how to solve determinants, so I'll give a refresher on that. And we'll have to include what's known as asymmetric or asymmetry wave functions, and talk about the Pauli exclusion principle or the Pauli principle and how that relates. So we're going to see some new terminology, but it's things that you all already inherently know. Okay? We're just going to express it in a different way. Before we get there, though, we should talk about the mathematics and something that we're going to use for the rest of the semester, determinants. You guys know what a determinant is, or how it gets represented? Yes, you definitely talked about it in linear algebra. Ellen, you took linear. Did either of you guys take linear? Okay. It's basically a simple way to express a complicated linear equation, and you represent this as a matrix. So a simple way. And okay, simple might be a little bit of an oxymoron here, but it is simpler. It is simpler. That's like, and your PChem book does this all the time, where it's like, it's simple to show, or you can show on your own. It's, what is it? It's very elementary to see that. And it's like, no way in hell is it. It took me 4 pages to derive this bullshit. You're lying to me. Like, I hate when books do that. So sorry, I'm doing the same thing. Complex linear equation. And it's a scalar that can be represented by a matrix. Okay. And they have different dimensions associated with them, right? So let's look at a generic 2x2. Okay, you get what I mean by 2x2 or no?
It's like a square.
Yeah, it's a square. We're going to have a total of how many digits for a 2x2? 4. Yep. Now the linear equation we're trying to represent is this equation. AD minus BC. And we can represent it in the following fashion. A, B, C. Does that make sense?
Yeah.
Okay. Let's look at a 3x3. So 3x3, how many terms do we have in here?
9.
Yep, we have 9. Okay. Now, what we have to do is we have to break this thing apart into smaller determinants in order to solve it. So I'm going to draw with some colorful chalk on here. And we'll hopefully not confuse this worse than we need to. Does anybody know how to break this thing down? Or remember how to break it down?
Wouldn't you first start with like A, B, D, E?
Yep, so you start with, let's start with A, so we're gonna have a term that starts with A out front. A, and then a smaller determinant in there. What's gonna be the smaller determinant? Or do people not know, and it's okay if you don't know?
I only know how to do it when the top line is like a vector direction.
Okay, how would you do it there?
Okay, well, we did like, you skip the first row and it'd be
Yup.
like EI minus FH,
Yep.
and then you do
That's-
the same thing for each one.
That's exactly what we're gonna do. So we're gonna skip this column and the first row.
Okay.
So, that bit is our determinant, 2 by 2 determinant. So we got E, F, H, I. And Lily, what you said about like subtracting them from one another, we're gonna get there in a second. Okay, what color do you wanna use next?
Blue.
Blue, oh, I heard blue first, sorry. Blue for B, there we go. Okay, so then we're gonna have a minus sign, then B, then we need a 2 by 2 determinant. What's gonna go in that 2 by 2?
D, F, G, I.
Yep. D, G, F, I. So we got D, G, F, I. Then we'll use red, race car red for C. Then we're gonna have it switches sign again to a plus. C, what's gonna go in that determinant?
D, E, G, H.
Yep. D, E, G, H. Okay? Let's evaluate this a bit further. Then we got A times, break this thing down.
E, I minus F, H.
Yep, so we're grouping, here is my plate. We're grouping these guys minus those ones. So what was it again?
E, I.
Minus,
FH.
yep. Then we got blue minus B times what?
DI minus GF.
Yep, DI minus GF plus C times what?
DH minus EB.
Yep. And then we would plug values in, and that's what we get out in the end. Or in some cases, we're gonna use expressions that have orbitals and other things in there, okay? People feel comfortable with that one? Okay, let's go to a 4 by 4. Okay, erase this. Four by 4. How many terms in a 4 by 4?
16.
16, yep. A, B, C, D, F, G, H, K, L, M, N, O, P. Okay, I'm gonna need more colors here. A, remember, we ignore the row and we ignore the column. So we're gonna have A, what determinant's gonna go in here?
F, G, H, J, K, L, M.
Yep. F, G, H, J, K, L, this is kind of a weird thing too. This came out of a book about Richard Feynman, but he found that there are some people that can like count and talk, but not read. And then there are some people who can read and talk in their head, but they can't count.
Like at the same time?
Yeah. Weird stuff. There's also people who do not have an inner monologue. That must be awesome. Or like I talked about the apple experiment with you guys before, right? Where people can't, like if you ask an apple what can they visualize, there's some people who just nothing, darkness. I think that's strange. Anyways,
How can you do organic chem if you can't?
that's why probably the organic chem failure rates are really high, or you really need to rely on models. And actually, they say that's why there's such a disparity between male and female scores in organic chemistry. Females tend to be way worse at three-dimensional representation than males. It's not true in all cases, because look at this room, it's...
I feel like in our order class, the girls seem to like that. I mean, there's
Okay.
just more of us too.
Well, the other thing is if you look at success in college, females are crushing it right now, so... Sorry, Will. But then it's like, what, 5 years, or well, last year, it was all the seniors, it was 5 females, so like, how does that work out? Yep. Alright, next one, sorry. We got B, another big determinant, what's gonna go in there?
E, I, M,
Got
G, K, and H.
sounds like we're speaking like a foreign language. Wow. Okay. Next one. Sign.
Wow.
Yep, positive. What are we gonna start with? C. I should have gone with red, but I didn't do that. Okay, what do we got for that one?
E, F,
Yeah.
H, I, J, L, M, N.
Yep. Now we're getting complicated. E, F, H, I, J, L, M, N, P, and then for the last one, what do we got?
D, oh, minus D.
Yep, minus D. What are we gonna have in that determinant?
E, F, G, I, J, K, L, M,
Yep. G. Okay. Then what would we do next if we wanted to solve this?
do the same as we did for the 3 by 3 for the 2.
Yeah, you would expand this and keep going that way. I like to do these by hand sometimes. You'll have to do one of these by hand for your final.
So fun.
Possibly, not this big, hopefully.
Oh, okay.
And there's other simplified stuff that happens in there. On homework questions, if you want to use a calculator to do it, feel free, but understand the process that's happening here. Okay? Let's do one where we actually have a numerical value, and we have you guys go through and try and solve it. Okay? Let me erase this. We're going to look at a 3 by 3. You get a different answer every year from each people.
Oh, well.
Evaluate the following. Yep, 3,
times 2, 6, 4,
6. Yep. Next one. What do we got for a sign? Yep. What number starts first? Yep. And then what do we got?
1, 6, 4, 3.
Yep. And then next one. What do we got, Lily?
2.
Yep. Sign. Oops.
Positive.
Yeah. 2, and then what's paired with it?
1 times, 1, 2, 4, 4.
Yep. Were you guys talking about doing crosswords or whatever, or yeah, you're like a champion at it. Will's got it.
It's like a math crossword. It's
Yeah,
weird.
exactly. It's like a Sudoku. It's like effortless. It's kind of nice. It's like one of those dumb Zen gardens that people have, where it's like the sand gets knocked around and you're like just ooh. My Zen garden. I don't know if you've ever done it. You know those big pink erasers. You get a razor blade and you just shave it. Super satisfying. You're gonna try it later. I know. Okay. This thing, let's break it down further. We got 3 times what?
6 minus 24.
Yes, so you multiply 2 times 3 minus 4, and we'll get to that too. Next one. Minus 4 times what? You're all scrambling to do it. 1 times 3 minus what?
6 times 4.
Yep. Next. Plus 2 times what?
1 times 4
Yep.
minus 2 times 4.
Yep. Okay. Run that through as you guys are already currently doing. What'd you get as a result?
I got 20.
You got 20?
I'm scared though.
I didn't use a calculator. I tried to do it by hand, so that might not be right.
So you got 6, 24, 3, 8, 18 minus 3, 72 minus 12 plus 8 minus 16 is what I got, I think. Go away.
I got 22, I think.
I got 22 when I did it out here. 6. How the hell did I do that?
Wait,
Oh, because it's minus 12. And I think you did 12 plus 8.
Oh, I did that.
yeah, so 3 times negative 18, right?
It's negative 56. Right?
Minus 12 here, plus 72.
Why is it?
Plus 8 minus 16.
Yeah, didn't I have that or not?
Yes.
So 72's cancel,
Yeah.
and then 18.
I'm missing something here. What did I screw up?
18 plus 8 is 20. Whoa, this is odd.
1 times 3.
I just computed the inside and then the short.
What was that?
Like I did like 6 minus 24 is negative 28. Or
So
negative
did I,
18.
but we got different
Negative
answers.
18 times 3 is 54. So then you you have negative 54,
Oh.
437.
That's where I'm wrong. I wrote 56.
And then you have,
Yes, you did.
I like did the subtraction before.
It shouldn't matter.
Now I also have 22.
Let me make sure. Okay, so negative 18 here, right?
And then the next one's negative 21.
Plus.
And then negative 2 times negative 4.
Yep. Okay, so then here.
Negative 54. Positive 84.
And
negative
negative 8.
And that is 22.
That is 22. What? Alright, let me stare at this thing. So I must have done something wrong here.
4 times 24.
Okay, so 3 times 6 is 18.
I think the 4 by 24 is wrong. I think that's the issue.
Oh, yeah,
So that's not
72 for
72.
that too. It's 4 times 24 for the second one.
It's
4
four-
times-
oh,
So it should
4
be
times
96.
24. Ah, okay, yeah.
Yeah.
There we go. Alright. Whew.
Yay, math! Okay.
It works! I got really scared for a second. Yeah, overall it should be 22. I've checked it several times. But that last little bit made me real nervous. Okay, you see how easy it is to fumble something up here though, which I just did. When it comes to the evaluation of things, on the final, you're gonna have a problem that's related to this, that you actually have to analyze and compute out. That's why I'm trying to give you enough time as possible. If the solution works out to be really tough, when we're talking about Huckel theory, chances are you botched it up somewhere in here, so just check it over again. Okay? Jeez. Everybody feels comfortable with this though, right? The more important point for what we need going forward is being able to transform back into this thing and to know what that determinant looks like. Okay? At least right now. No other questions? I hope that's zen-like for your mind, especially as we get closer to finals. Okay. So what we're going to do next is we're going to talk about the Pauli exclusion principle and to factor it in to our wave function, and then we're going to use a determinant to express the wave function for the helium atom. The Pauli exclusion principle. Okay. You guys probably know a definition or a way to explain the Pauli exclusion principle. Does anybody have a way that they formulated it in the past? Or how have you explained it to people in Gen Chem?
I know it's one of two things,
Okay,
but I always mix up which it is.
sure, let's go for it.
Okay, so it's either the spin of the electrons in one shell has to be opposite, like they can't be two of the same spin, or it has to be that you have to fill one in each before you can double.
So the one in each is Hund's rule. The
Okay.
first one that you said, where they have to have opposite spins, is true.
Okay.
You can go a little more generically and talk about quantum numbers. Electrons cannot have the same set of quantum numbers.
Yes.
If they do, you're going to violate asymmetry. So one that you guys have probably used before and have used a lot is no more than 2 electrons may occupy a given orbital and then if two electrons do occupy an orbital, what must be true about those electrons?
They must have different times of best values.
Yep, they must have different m sub s values, different spins. Do occupy. Then their spins must be paired. Meaning spin up, spin down. Okay. Or there's another way to express this, and this is a more physicsy definition. Have you guys ever heard the term fermion?
I think so.
Have you heard bosons? Okay. What subatomic particles do we almost always deal with in chemistry?
Electron.
Electrons.
Protons, neutrons.
What's that? Protons and neutrons. There are way more subatomic particles out there than that. It's just most of the matter we deal with is built of those things. Do you know any other subatomic particles?
Alpha.
Isn't there?
Yeah.
There's
Alpha particles, which is really like a helium atom.
There's like neutrinos or something.
Neutrinos, yep. Neutrinos. There's pions, muons. There's positrons, so things that have opposite charges of electrons. Tachyons. It sounds like I'm just making words up, but seriously, there are a large number of subatomic particles.
The entire Greek alphabet.
Yeah.
Electron on
Yeah,
that.
basically. In undergrad, I worked on a model for particle collisions called the non-commutative Lorentz-conserving standard model of particle collisions, which I learned a lot about subatomic particles at that time. I also learned that everything is mathematics from that. It didn't get adopted, or else that would be the new standard model. We just call it the standard model, but it's out there. So there are things called fermions and bosons. And do you have any physics friends that have talked about quantum electrodynamics? Which that also just sounds like a giant word salad. It is an actual thing. It's really looking at charged particles and other things at really small levels. And Richard Feynman whined on about in the past, he had looked at some of those things. But when physicists were originally concerned with this stuff for quantum mechanics, they didn't really know what was the right solution. So they had things that were fermions, things that have half spins, and things that are bosons, small particles that have full spins. So values of 0, 1, 2, and then there were fermions that had 1/2, -1/2, +3/2, and so on for their spins. And they had experimental evidence for those things, and it was really confusing. So we're going to write the physicsy definition for the Pauli exclusion principle, which states, and the labels any two fermions, identical fermions are exchanged. The total wave function sign changes. When two identical bosons are changed or exchanged, the wave function sign does not change. Oops. conventionally, chemists utilize this one because it's an easier way to describe it to themselves. Physicists tend to use the other side. When we were talking about pairing energies, or when you were talking about pairing energies in inorganic, the topic of electronic exchange came up. I've talked about electronic exchange in lab and in here a little bit. This is what electronic exchange is. So when you hear about exchange energy, that's what we're talking about here. There's no classical analog. It's a complicated idea. And we're just trying to use one word to explain what's going on here. Okay. That probably doesn't mean anything to you right now. But what we're going to do is we're going to go through a proof to try and show that this is true and how to relate it to, how to relate it basically to that picture for the helium atom. Okay? There's a lot of stuff that's going on here that you know, but we just want to show it. Okay? Everybody feel like they have an idea of what we're going to do for the rest of class, or at least where we're trying to head. We're trying to show that this is true. We're going to use helium as an example, and we're going to build a wave function that is actually a determinant to do that. Okay? If you get lost or you have no idea what the hell is going on or why we're doing it, say something. We'll refresh what we're trying to do. I am hoping by the end of class it will make sense and you'll get to see it. Okay. So we know the Pauli exclusion principle, or at least I've told you since general chemistry has to be followed. We're going to try and show that. To do this, we're going to consider a wave function of a two-electron system. So our wave function, we could say R12. I'm just going to leave it as 1, 2. Does that make sense? Okay. If we exchange labels, so I switch the labels of 1 and 2 around. What needs to be in front of this wave function in order for that to be true, since we're talking about electrons, which are fermions?
Negative sign.
Yeah, there should be a negative sign here. Okay. We run into a problem with two electron systems in terms of the math, in terms of the Hamiltonian. What's the problem with two electron systems? What do we have to worry about? Them interacting with one another. What approximation do we use to get around that? Yeah, we use the orbital approximation. So, using the orbital approximation, how would I represent this?
Like phi, or like the first one.
Yeah, we would use phi. If we have a two electron electron system like helium, what do we know about those orbitals, or what label would we give to a helium atom? So if we were to draw the electron configuration diagram, we'd have something like this, 1s. So what we want to indicate along here, I'm just going to put it in a different color for now, but we'll switch it back, is a 1s. But what information are we lacking?
Which one's the spin up and just spin down?
Right, we haven't talked about spin. In order to do this right, we need to include spin. We must include spin. From a handful of other experiments, but the Stern-Gerlach experiment showed us that electrons have inherent spin to them, so we gotta worry about that. We have two parts to a wave function. We have the spatial or the orbital function, the 1s, and then we have spin functions. The spin part of the wave function is denoted here. What are we going to use to denote spin up and spin down? Or what did we do in the PMR lab?
Oh, alpha and beta.
Yeah. So we have spin orbitals too, called alpha and beta. And what does that depend on? What quantum number?
Mhm.
Yeah. Okay. So now we gotta think of all the possibilities that exist for the approximate wave function for the system. Possibilities. I'm going to write one, and we're going to come up with the other ones. So, our spatial orbitals, or orbital wave functions, what labels are they going to have?
Like the 1s.
Yep. We're going to have 1s. Electron number 1's in that 1s. And then we typically have the spin orbital next to it. For the first electron, what spin do you want to give it?
Alpha.
I want alpha 2. So we do alpha 1 times 1s 2, and then what about the spin? Yep. Okay, what else could we have?
The other way around. Where one is one is beta and two is alpha.
Mm-hmm. Oops. What other possibilities could we have? is a possibility. Is it one that's gonna work out?
No,
Why not?
it can't be the same spin.
Yeah, it can't be the same spin, Pauli exclusion principle. However, let's pretend we don't know anything about the exclusion principle right now.
Okay.
And what's another possibility that we could have?
Bigger.
Yep. Okay. So these guys, remember, they're called what type of orbitals? What do they keep track of?
Spin.
Yep, so they're called spin orbitals. And oftentimes, these are called spatial. Or often just sometimes orbitals, which make things really confusing. Next time, what we're going to do is we're going to rule some of these things out. One with a little bit of experiment, one with some other observations. Which ones are we gonna knock out?
Last one.
Yeah, these two, and then we're going to show a relationship between these guys. And what it will work out to, these are actually going to be determinants, once we want to simplify it. Okay? Are there any questions right now? Okay. Next time, we're going to take these complicated ideas, express a wave function as a determinant, and that's how we just have to express wave functions from here on out. The nice thing is it is mathematically too intense to have anybody calculate these things by hand. So that's where we do computer stuff, and that's what the computers are doing in lab for you guys. So the mathematics is pretty much just done at this point.